For our project, we implemented a variation of the popular arcade game Pacman, using ChipKit Max32 microcontrollers controlling Zumo rovers. Our goal was to have a fully autonomous game consisting of one Pacman rover playing against two Ghost rovers. The game takes place on a 4-foot by 6-foot enclosed maze with a grid pattern. The walls of the maze are 5 inches high, and the paths of the maze are 10 inches wide. The paths of the maze are clearly defined with black lines, and the intersections are defined with black boxes. The game begins with a yellow Pacman rover and the red and purple Ghost rovers starting off at different points in the maze. The Pacman rover must roam around the maze, avoiding the two Ghost rovers. The Ghost rovers attempt to catch the Pacman rover while avoiding collisions with each other. The Pacman rover earns points every time it crosses the intersection and will continue to roam around the maze until it is caught by a Ghost rover. The Pacman is considered caught by a Ghost when the Pacman and the Ghost are moving towards the same intersection in different directions, at which point the game will end. Our block diagram shows the hardware design for each rover. At the base of our rover is the ChipKit Max32 microcontroller board running FreeRTOS, a cross-platform real-time operating system. On top of the microcontroller lies the ChipKit PMOD shield, an input-output expansion board that provides additional connectors for peripheral modules. On top of the PMOD shield is the ChipKit motor shield, another expansion board that provides additional circuitry to drive various types of motors. On top of the motor shield lies an Arduino wireless shield with an attached Wi-Fi, providing the rover with wireless communications to a server. Additionally, each rover has 4 sensors, 3 infrared proximity sensors, and 1 QTR8 reflective sensor array. The infrared proximity sensors made by Sharp have analog outputs that vary from 3.1 volts at 4 centimeters to 0.3 volts at 30 centimeters. These sensors are powered through the connectors on the PMOD shield and output their values to the analog pins on the Arduino wireless shield. The QTR8 reflective sensor array is used as a line follower. The sensor outputs 6 digital I/O compatible signals that are read as a timed high pulse. The sensor is powered through 5-volt and ground connectors on the Arduino wireless shield and use 7 general purpose input-output pins on the microcontroller. The microcontroller and extension boards sit on top of a battery pack attached to our rover. Plastic mounting boards surround the rover in a box formation. The infrared sensors are mounted to the front, left, and right of the rover to detect walls and open paths in the maze. The line follower is mounted to the front of the rover, facing the floor to detect path and intersection markings below the rover. Our task diagram describes the software threads and communication between each thread. The sequence of tasks starts with a FreeRTOS timer interrupt that occurs every 50 milliseconds. This timer interrupt service routine pulls the sensor data from the 3 infrared proximity sensors and 1 line follower sensor. This sensor data is sent to the sensor thread via a FreeRTOS message queue. The sensor thread interprets the sensor data and sends it to the USART thread through a second FreeRTOS message queue. The USART thread constructs the data received from the sensor thread as a packet for an interrupt-driven transmission to a server hosted on a Raspberry Pi through a Wi-Fi. The server will respond with a motor command based on the sensor data it receives. A USART interrupt will occur when a command is received and will send that command to the motor thread through a third FreeRTOS message queue. The motor thread carries out the command received from the message queue by driving the motors using pulse width modulations and reads encoded data using the external interrupt. The sensor thread also has the ability to send motor commands to the motor thread through a FreeRTOS message queue to adjust the motors based on the line sensor's values. The sensor thread uses data from all 4 sensors to determine the state of the environment surrounding the rover. The 3 infrared sensors can detect objects 4 to 30 centimeters away. These sensors are used to find the walls and open paths within the maze. The line follower sensor determines if the rover is on a path or at an intersection. If the line follower sensor is on a path and the infrared sensors detect objects to the left and to the right of the rover is currently traversing through a corridor of the maze. If the line follower detects an intersection, the infrared sensors are used to determine which directions are blocked and which directions are open. The rover can encounter 6 types of intersections. When the rover approaches an intersection, the type of intersection is sent to the server, which responds with an appropriate motor command. When the rover is on a path, the line follower can determine if the rover is veering to the left or to the right of the path. If the rover is moving forward, the sensor thread can send a motor command to adjust back on path.
Our rovers include 2 micro metal gear motors that are attached to the Zumo rover chassis, one for each tract. It also includes two magnetic encoders which are attached to the inside half of the motors. The magnetic encoders send back values that can be converted into distance the rover has traveled. It also takes in motor commands from the motor shield that's mounted on top of the chip kit to execute on the motors. Basic motor commands include the following. The rover is able to go forward, turn left 90 degrees, turn right 90 degrees, turn around 180 degrees, and also go in reverse. The rover is also able to make adjustments left and adjustments right so that it stays centered on the line. This is done using pulse width modulation. Pulse width modulation allows us to operate the motors at varying speeds. This allows us to set the motor to either go faster or slower. Here you can see that with a larger duty cycle, the motor is on for a longer period of time than it is off. This means that the motor will move at a faster speed. With a smaller duty cycle, the motor is on for a shorter period of time and off for a longer period of time. This means the motor will operate at a slower speed.
Alright, I'm going to run you through the user interface of our project, which is a program written in Python using PyQt, a binding of the Qt framework, and running here on a Raspberry Pi. So from the command line, I'm going to start up the program. And first you see an initialization window that has drop-down boxes for the X position, the Y position, and the heading of each of the Pacman, Ghost 1, and Ghost 2 rovers. You can set this to however you've got the rovers configured on the game board, and when you're happy with that, you can click OK. If you've made a mistake, you can click Reset, which sets them all back to 0, 0, heading north, or you can click this Use Defaults button, which will set all of the coordinates and heading to default values specified in the code. So you can hard code in a specific layout that you like and click this button each time you run the program, so you don't have to enter all of them in manually. I've got the rovers laid out on the board myself in this default configuration, so I'm going to go ahead and click the Use Defaults button. Now the next window that pops up is your main control window, which has a lot of buttons and displays, but there's not really any information going on right now. That's because I haven't clicked the Start button. So when I click the Start button, the server status goes to running, and we can see output from all of the rovers. So this tab display has one tab each for Pacman, Ghost 1, and Ghost 2. And these displays display the IP address, the IR sensor readings, the coordinates, heading, current commands, IR status, and line follower status pictures, which are pretty useful to give you an idea of what they can actually see right now. Now, in order to start the game, you've got these two buttons down here, the manual override button and the automatic mode button. You're going to want to click the automatic mode button, which I'll do right now, and you can see that all of this data is updating, the IR status picture, the line follower status picture, they're updating, and the rovers are currently running. So this is what you'll be seeing during the bulk of the game. Now I'm going to click manual override, and this button is used when the rovers get into a bad situation and you need to control them yourself. So you'd go here to this manual control tab where all of these control buttons are now available to click. So you can send rovers forward, left, right, backwards, and have them do a little bit of an adjustment left and right. And you can do that for each of them individually, no problem. Get them back online, and then you can click automatic mode to get back into the main game mode. Now when the game is over, it will automatically stop, and the server status will say game over, and the score will turn red. But if you want to end it yourself, you can click the stop button and see the same thing. So the server status is now stopped, the score is 2 displayed in red, and your game is over. So that is a general overview of our user interface.
Our gameplay algorithm includes two main components, the Pacman rover and two Ghost rovers. Our Pacman rover's only job is to run away from the Ghost rovers, while the Ghost rover's job is to chase after Pacman while still avoiding the other Ghost rover. The game will come to an end when the Pacman is cornered by another Ghost rover headed to the same coordinate that it's headed towards. While developing the gameplay algorithm, there were certain unique features that we needed to add so that the game would run smoothly. One of them was that we had to give the Ghost rovers the capability to turn around so that they wouldn't collide into each other. As you can see in the video, they were headed to the same coordinate, and since they would only be able to go towards the middle intersection, this Ghost rover had to make a U-turn so he would go back to the way he came from. Another unique feature that we added for the game was that Pacman was allowed to run away from the ghosts, even if they're headed to the same coordinate, as long as they're in the same heading. So here you can see that they're both headed to this coordinate, but Pacman is running away from the ghost, so it allows him to continue going without the game coming to an end. After extensive testing, it is known that the game will run as long as Pacman has not yet been cornered. Since there's still a factor of randomness to the game, the highest record that we have gotten so far is 17. Manual override mode will also fix the occasional issue when a rover goes off path, allowing this game to run smoothly as long as it can. Reliability throughout the semester was a tad bit of a struggle for us, only in terms of physical hardware sensors and the motors. This is mostly due to the fact that we were handling the rovers for long periods of time during testing, picking them up and putting them back down on the maze. This caused a lot of stress on the components and could have been the fault of the human as well. A possible area of improvement for our project would be to make the game board bigger. This would allow the game to run longer, and it would be more interesting as the rovers would now be able to take more options when they come to an intersection. Another thing is implementing manual control mode earlier. This would just help us with testing the code and testing the gameplay algorithm when it all came to an end near the end of the semester. Another thing is implementing robust motor controls. This would have helped us on during our earlier stage when we were initially testing with lackluster motor commands where the adjustments weren't based off of pulse width modulation. This caused the rover to make zigzag turns and would always throw it off every time it got to an intersection.